Good evening. It's 19 past 7 in Moscow, so I think it's time to begin. It's a pleasure to introduce our today's speaker, Evgeny Ferapontov from Lavro University, and he will speak about involutive scroll structures and solution of four-dimensional integrable hierarchies. Well, Evgeny, you're welcome. Please begin.
Thank you, Osif. Thank you for inviting me. Can you hear me? Can you see everything? Yeah?
At least I can hear you perfectly.
Excellent. So the work is based on joint paper with the talk is based on joint paper with Boris Kruglikov. So we will introduce involutive scroll structures on manifolds, and then we will describe all these structures, involutive scroll structures in low dimensions, in terms of some dispersionless hierarchies of the self-duality equations. Okay, so I will define everything in detail. Right, so let me start with a general picture. Suppose we have a PDE system, we call it sigma. Then every solution of sigma defines some geometry via the characteristic variety. So the system has characteristic variety. It depends on the solution. So different solutions have different characteristic varieties, and this characteristic variety defines geometry on every solution. It can be Einstein-Weil geometry, self-dual geometry, involutive scroll geometry, and so on. I will define everything later, right? So with every solution of every PDE, I can associate certain geometry via the characteristic variety. For instance, if you take the simplest thing you can think of, take, say, two plus one dimensional wave equation, UTT equals UXX plus UYY, just linear wave equation. Then its characteristic variety is PT squared equals px squared plus py squared. PT, px, py is a characteristic covector. Right? So this equation, this is a quadratic equation. It defines a quadratic characteristic cone, right? So in other words, for every solution, we have this characteristic cone, but it's a flat geometry because there is no dependence on the solution, right? It's typical for linear equations. Characteristic variety is the same for all solutions. It depends on the system, on the equation. It doesn't depend on a particular solution, just one and the same for all solutions. But for nonlinear systems, the fields will enter the equations of the characteristic variety. So characteristic variety will vary from point to point, right? So let's fix some geometry, like Einstein-Weil, self-dual, involutive scroll geometry. Let's fix some geometry. I will call a PDE system a master equation for this geometry if characteristic varieties of this system give all geometries of this kind, right? And I will go through 4 examples of these master systems. For instance, the first 3 are known, and the 4th one, this one, involutive scroll, is a new one. So, for instance, self-dual Ricci flat geometry in 4D. We have 4-dimensional metrics, which are self-dual, so half of the conformal Weil tensor of conformal curvature is 0, and Ricci tensor is 0. Self-dual Ricci flat geometry, something studied in general relativity. So it is known that every such geometry is described by Plebanski's heavenly equation, first or second. So I'll go through this in detail and show you the formulas later. Right, so Plebanski's heavenly equation is master equation for self-dual Ricci flat geometry. What is important that this geometry, this conformal structure, is characteristic variety of the heavenly equation. So this geometry is a characteristic variety, That's important for in our construction. Then, okay, Einstein-Weil geometry in 3 dimensions. It turns out that every such geometry is described by the Manakov-Santini system, by certain explicit formulas, which I will show. In other words, Manakov-Santini system is a master system for Einstein-Weil geometry in 3 dimensions. Right, and again, Einstein-Weil geometry consists, it's geometry based on a certain conformal structure in 3 dimensions. So this conformal structure is characteristic variety of the Manakov-Santini system. Then self-dual geometry in 4 dimensions. It's just a generalization of the first geometry. We just cancel this Ricci flatness. Drop this Ricci flatness requirement. Just self-duality. 4-dimensional metrics with half of their Wall tensor 0, right? Such systems, such metrics were, such conformal structures were discussed by Penrose. He studied them in detail, and it turns out that this geometry is described by the so-called conformal self-duality equations, which I will show. All right. So in other words, conformal self-duality equations are master equations for self-dual geometry in 4 dimensions. Again, this conformal structure is a characteristic variety of conformal self-duality equations. And the most general geometry that I will discuss, involutive scroll geometry, I will define this. In general, scroll is just another word for ruled surface. And what involutive means, I will say in due time. And it turns out that this geometry is described by the hierarchy of conformal self-duality equations. So conformal self-duality equations themselves, they define self-dual geometry, and the hierarchy of these equations, they define involutive, it defines involutive scroll structures. And so my talk is, so these first 3 are known, and probably I even spoke about them at some time at this seminar. And this is new, right? And it's based on our paper with Boris. Okay, so let me start with the first, with self-dual Ricci flat geometry. Oops. Can you see full slide? Yeah?
Yes, Zhenya, everything is seen, yes.
Good, good. So this is Polybansky's first heavenly equation, right? It's a Monge-Ampere scalar Monge-Ampere PDE for one single function u, depending on x1, x2, x3, x4, 4 independent variables. And uij, this mean partial derivatives. Yeah. So it's a well-known PDE. Its characteristic variety, in other words, collection of characteristic covectors, pi dxi. So we have characteristic variety has components p1, p2, p3, p4. Characteristic covector has components p1, p2, p3, p4. And this, it's defined by this equation, right? It's a quadratic equation for p's, all right? So let's write this equation in indices like this. Gij, pi, pj. Then Gij is a certain symmetric matrix, right? It's a quadratic form. It corresponds to a symmetric matrix, Gij. I treat this, you see, pi's, they have low indices. So Gij, they have upper indices. Gij is the kind of contravariant metric with upper indices. The inverse of what we know as Riemannian metric. Okay, so this characteristic variety is defined like this. You substitute for u, you substitute u plus epsilon v, right? Where epsilon is a small parameter. So and u is a solution to this equation. So you take formal linearization of this equation. You substitute u plus epsilon v and keep terms at epsilon. You'll get a linear equation for v. It's a kind of linearized equation on the background of a certain solution, right? So this linearized equation has a symbol, and this is its symbol, right? This is the symbol of linearized equation. Okay, so now we have this equation defines us a 4x4 symmetric matrix with upper indices, right? Let me take its inverse. I call it Gij. Yeah, it's also a symmetric matrix, inverse of this matrix. Okay, it's easy to calculate this inverse, and then you contract it with dxi dxj. So this gij with low indices defines you a metric on x1, x2, x3, x4 space, on the space of independent variables. So in other words, every solution of Plebansky defines you this metric. And this correspondence, it makes invariant sense because this comes from the principal symbol, right? It turns out that this metric is self-dual and Ricci flat. So half of its Weil tensor is 0. Self-duality conditions, I'll write them explicitly later, somewhat later. I'll show you how to calculate them. And Ricci flat is just, Ricci tensor is 0. So, and then it was proved by Plebansky that every self-dual Ricci flat metric arises in this way. So you take a solution of this equation, you put it in here, and you get self-dual Ricci flat metric, right? So in other words, this equation is master equation for all self-dual Ricci flat metrics, and they arise via the characteristic variety. Okay. It's well known that Plebansky's equation has a Lax-Payne vector fields. Here, lambda is an auxiliary spectral parameter. Yeah, lambda appears here and here linearly, and there is no differentiation by lambda in this Lax pair, right? And it turns out, okay, that fix lambda, then these vector fields, they commute for every solution of Plebansky's equation. So for every solution of Plebansky's equation, these vector fields commute. So they form an integrable distribution. So they have integral surfaces, two-dimensional surfaces, right? For every fixed lambda, you have integral surfaces of this distribution spanned by xy. It turns out that these integral surfaces are null for this metric, What does it mean? It means that the restriction of this metric on these two-dimensional surfaces is just identically 0, not just degenerate, identically 0. In other words, g of xx is 0, g of xy is 0, g of yy is 0. This holds, all right? And it was proved by Penrose that self-duality of a metric is equivalent to the existence of this, what he called totally null surfaces. Three-parametric family of totally null surfaces. Why three-parametric? Because, okay, if you fix lambda, yeah, lambda is one parameter, but let's fix this parameter. Then you have two vector fields in 4 dimensions. They have two-dimensional integral surfaces. Obviously, these surfaces depend on 2 parameters because we are on 4 dimensions. We have a foliation of 4 space by 2-dimensional surfaces. There is a 2-parametric family of them, and also lambda is the 3rd parameter. So we have a 3-parametric family of totally null surfaces. According to Penrose, this is equivalent to self-duality. And you see these totally null surfaces, they come from the Lax pair, just integral surfaces of the Lax pair, right? So this is one picture, the first picture. So for self-dual Ricci flat geometry. This master equation is not unique. For instance, if we take this second heavenly equation and do exactly the same thing, calculate its characteristic variety, like this, analogous variety, construct the corresponding metric, then it will also be self-dual and Ricci flat. So in other words, this is another master equation for the same geometry. Master equation is not unique, but clearly, since these two PDEs define one and the same geometry, they must be equivalent in some way. Indeed, there is a backlund between first and second heavenly equations. It's quite non-trivial. It's quite a non-trivial backlund. It's not a contact equivalent, not contact equivalents. They're not contact equivalent, but there is a backlund between them. All right, so master equation in general is not unique. All right, so let me move on to the second geometry, second example, Einstein-Wall geometry in 3 dimensions. In this slide, I'll just define Einstein-Wall geometry and tell what is known about it. So we are in 3 dimensions, now on 3 manifold. In principle, Einstein-Wall geometry is defined in any dimension, but only in 3 dimensions, it's integrable. It's kind of described by integrable equations. In the other dimensions, it's not integrable. In 2 dimensions, it's just not of interest, right? So Einstein-Weil geometry is a triple. You have a conformal structure G, a covector omega, and a certain symmetric connection D, not Levi-Civita connection of the metric, just some symmetric connection. So connection, conformal structure, and the covector in 3 dimensions. And they must satisfy these 2 equations, sets of equations. Right, first of all, covariant derivative of metric is proportional to the metric. These are called Weil equations, Weil's equations, right? If omega is zero, then we get covariant derivative of the metric is zero. It's called Levi-Civita property, Levi-Civita connection. But if omega is non-zero, it's called a Weil connection, right? So dk is a Weil connection for the conformal structure G. And this is symmetrized Ricci tensor of this connection. Is proportional to the metric. This is Einstein's equations. So these are Weil equations, these are Einstein's equations. That's why it's called Einstein-Weil geometry. Right? In general, a Ricci tensor of Levi-Civita connection is always symmetric. But this D is not Levi-Civita. So its Ricci tensor doesn't need to be symmetric. We have to symmetrize, right? So these are Einstein-Weil equations. I think they were introduced not in the context of general relativity. This geometry was introduced by Cartan in the context of in geometry of third-order differential equations. Right? I don't know whether they are really relevant to general relativity, but Einstein-Weil geometry is a reduction, symmetry reduction of self-dual geometry, which is relevant to general relativity. Right? So symmetry reductions of self-dual metrics in 4 dimensions gives this geometry. All right, well, it's a conformal geometry. If we keep D unchanged, rescale G, and change omega like this, right, then these equations still hold, right? They don't change, these equations. So that's why we're allowing to scale the metric. Lambda is, by the way, not a constant. Lambda is an arbitrary function. So we are allowed to scale the metric. That's why this geometry is conformal. Now, what Cartan proved? He proved that this he established geometric meaning of these equations. He proved that this triple dg omega satisfies these equations if the following holds. If there exists on this 3 manifold where these things are defined, there exists a 2-parametric family of surfaces, 2-dimensional surfaces. So let me try to draw something here. Yeah? I never tried this before. Oops, I can't for some reason. Wait a sec. No. Okay, it doesn't work. Sorry. Sorry, let me try. No, for some reason I can't draw now. Okay, I know. I know. Let me try again. Okay. So this is a 2-dimensional surface. Can you see it?
Yes, Zhenya.
Okay.
Your picture, yes?
Yeah. And
yes,
this
yes.
is they're in 3-dimensional manifold, M3. It's a 2-dimensional surface. And we have 2-parametric family of such surfaces. So we have many of them like this, yeah? Like many of them. 2-parametric family. So each of these surfaces must be totally geodesic in this connection. What does it mean? It means that if I pick a point on this surface and I pick a tangent direction to this surface at this point, then and I can construct a geodesic in terms of this connection, right? In the ambient space M3. So the property is it must lie on this surface, right? So geodesics starting on the surface and in the tangential direction, they lie on the surface, they stay on the surface. This means totally geodesic. For instance, in three-dimensional Euclidean space, let's take a sphere, for instance. Take a north pole, the north pole of the sphere, and take a tangent direction at the north pole to the sphere, right? Let's construct geodesic in 3 dimensions through the north pole in this tangential direction. It will be a straight line. It clearly escapes from the sphere immediately, right? It doesn't lie on the sphere, right? So sphere is not totally geodesic in 3 space. But if you take a plane, 2-dimensional plane in the usual Euclidean 3 space, take a point on this plane, take a tangent direction to the plane, so there's some vector on this plane, then draw a geodesic through this point in this direction. It will be a straight line. It will stay in the plane. Usual plane is totally geodesic in 3 space, right? So, okay, this surface must be totally geodesic, first condition, and then it must be null with respect to this conformal structure or metric to G. What does it mean? If you restrict G to this 2-dimensional surface, you can't get something identically zero in 3 dimensions, but you can get something degenerate. If your metric on restriction to this 2-dimensional surface becomes degenerate, then the surface is called null. So in other words, Cartan proved that this triple satisfies these equations if there exists a 2-parametric family of surfaces which are totally geodesic in this connection D and null with respect to G. And he also proved using Cartan method of moving frames that such structures depend on 4 arbitrary functions of 2 variables, right? And then later Hitchin proved that Einstein-Wall equations are integrable by a twistor construction, right? This is all quite implicit. Let me show you, write some formulas where we will see everything very explicitly. All right, so let's go to the next slide. Okay. Now I have it permanently. Right, let me try to erase it. Sorry. Okay. Okay, better. So let's go to the next slide, Manakov-Santini system. Yeah, there is one more. Okay. So what is Manakov-Santini system? We have 2 functions, u and v. Functions, u is a function of xyt and v is a function of xyt. So let's introduce this differential operator, second order differential operator. It depends on u and derivatives of v, right? And then we have two PDEs. P of v equals 0. You apply this differential equation for v, you get a second order PDE for v. And then you apply, by the way, nonlinear because we have v coefficients here. And you apply this equation for u. This operator for u plus ux squared equals 0. So this pair of equations, it's 2 second order equations for u and v. It's called Manakov-Santini system. It was introduced in the attempt of Manakov and Santini to generalize DKP equation, dispersionless KP, as much as possible, right? In particular, if you set here v equals 0, then this equation disappears and this becomes DKP, right? So what is the characteristic variety of this system? So you see, since the leading parts of both equations are the same, it's the same P applied to U and V, right? The characteristic variety is a quadric, but we have to count it twice. It's a double quadric, right? And it's given by this equation. It's quadratic equation in the components of covector Px, Py, Pt. Before I was denoting covector P1, P2, P3, P4. Now I denote variables x, y, t, and it's Px, Py, Pt. Right? Characteristic covector satisfies these equations. Right? These equations define a this equation is a quadric, so it defines a a 3 by 3 symmetric matrix with upper indices. I invert this matrix, so I get a 3 by 3 symmetric matrix with low indices. And this matrix defines me a metric, this one, G. It's a conformal structure. So this G is a characteristic conformal structure. And Maciej Dunajski, he observed that if you introduce a covector omega in this way, right, and then you introduce connection. By the way, let me go back to this slide. If you know G and omega, then you can calculate this connection uniquely from this equation. This dk is defined uniquely by these equations, right? So once you know omega and G, you define D. So it's enough to define actually these two. This D is defined by the Weyl equations. So right. So once you have G and omega, you can calculate this connection, and then it turns out that this thing, dg and omega, gives you Einstein-Weyl structure. And then we proved in a joint paper with Maciej and Boris that all Einstein-Weyl structures arise in this way. So Manakov-Santini system is a master system for Einstein-Weyl geometry, right? There is one subtlety here that we still don't quite understand, right? Einstein-Weyl geometry, it has two main objects, G and omega. G has a very intimate relation to this system, namely it's just the characteristic variety, right? Characteristic variety. But omega is a little bit more mysterious, and we still don't know an invariant kind of meaning of this omega. What is it in terms of the PD? It's certain subsymbol, but we don't have a precise kind of statement about omega. So, for instance, if you have this system, right, this system, you can make any change of variables, any backlund, doesn't matter. Then if you calculate in the new coordinates, after making a backlund, you calculate characteristic variety, it will still be a double quadric, and it will be the image of this. It will be equivalent to this, right? Because symbol is invariant under every transformation. Backlund, point, contact, doesn't matter, right? But this omega, we don't know how to calculate it in the new coordinates, how to recalculate it. So what is its precise geometric meaning? It's still an open question, right? But okay, it turns out, let's introduce these two vectors, Lux pair for the Manakov-Santini system. Note that this time it contains d by d lambda. It has differentiation by spectral parameter, and lambda appears quadratically here. Lambda squared, lambda, and linearly here, lambda. Right? It turns out that this equation, commutativity of these vector fields, is equivalent to Manakov-Santini system. Right? It's equivalent to this system. So it's a Lux pair, dispersionless Lux pair of Manakov-Santini. Okay, let's then consider these two vector fields in this ambient space, in this extended space of x, y, t, independent variables, plus lambda, plus spectral parameter. Sometimes it's called correspondence space. Okay, this is a 4-dimensional space. We have two vector fields. These two vector fields commute. Their commutator is 0. So they define a 2-parametric family of surfaces in this 4-dimensional space, right? 2-parametric family. Because we have foliation of 4-dimensional space by 2-dimensional surfaces. There is 2-parametric family of them. Okay, so let's project them down to the x, y, t space just by forgetting lambda. Project them down, right? Then we get a 2-parametric family of surfaces, 2-dimensional surfaces on x, y, t space. It turns out that these are precisely Cartan's 2-parametric family of totally geodesic null surfaces. So again, they come from the Lux pair. Right, these geometric objects, they come from the Lux pair. In other words, this Cartan's theorem that this triple satisfies Einstein-Weyl equations if there exists a 2-parametric family of surfaces, implicitly it postulates the existence of a Lux pair, because these surfaces come from the Lux pair, right? But of course, there was no such language at that time. Okay, one more comment. Cartan, remember, Cartan proved that generic Einstein-Dual structures depend on 4 arbitrary functions of 2 variables. In this particular case, it's easy. It's very easy because Einstein-Dual geometry is defined by a pair, by 2 second-order equations. Well, if you have 1 second-order equation, its solution depends on 2 functions of 2 variables. If you have 2 second-order equations for 2 functions, then the freedom is 4 functions for 2 variables. Each equation brings 2 functions, right? So this freedom is obvious once you parameterized everything explicitly. Okay. Let's move on to another third example, self-dual geometry. So now we are in 4 dimensions, and G is a conformal structure. Let W be its Weyl tensor. You know, in 4 dimensions, conformal Weyl tensor of conformal curvature, it splits into 2 halves, right? Self-dual, anti-self-dual. And we have this W plus minus are the self-dual and anti-self-dual parts. What is it? It's W Weyl tensor plus minus. It's Hodge dual, star W, where this star W is defined by this explicit formula, right? This is star W, root of determinant G with upper indices, and this is a totally skew symmetric tensor, right? With epsilon 1, 2, 3, 4 equals 1, and then you change the sign when you permute indices. All right. So in the conformal structure, G is said to be self-dual or half-flat, self-dual or anti-self-dual, if either W plus or W minus vanishes. All right. Then Penrose proved that a conformal structure is self-dual if and only if there exists a 3-parametric family of totally null surfaces on this 4 manifold. 3-parametric family of totally null surfaces. We discussed them before. So totally null in this context, it means that when you restrict the metric to your surface, it becomes just identically 0, not just degenerate, identically 0, right? And then Grossman showed that self-dual structures locally depend on 6 arbitrary functions of 3 variables. Okay, this is again quite implicit, these 2 characterizations. Let me parameterize now everything in coordinates, right? And we will see where the number 6 is coming from, and we will see that this 3-parametric family of totally null surfaces, they come from the Lux pair of the corresponding system, right? So, okay, next slide. Now we introduce the so-called conformal self-duality equations. These are equations in 4 dimensions. So we have coordinates independent variables x1, x2, x3, x4. And we have 3 dependent variables, u, v, and w. So you see u, v, and w. They are functions of these 4 variables. We introduce the following second-order operator R. This is second-order operator. You see its coefficients depend on u and v functions, on their derivatives, right? And then conformal self-duality equations is this 3 equations, is the system of 3 equations. So it's these are 3 second-order PDEs for u, v, and w, right? 3 second-order partial differential equations in 4 dimensions. Okay, since the leading parts of each of these equations is kind of one and the same, because R is one and the same operator, the symbol of this 3-component system is a triple quadric. This is the symbol, right? But this quadric has to be counted 3 times because it's kind of it appears in the first, second, and third equation, the same, unchanged, the same R. That's why each of these R's, it defines, each R defines this quadric, and there are three of them, right? We have to consider this 3 times, right? The coefficients of this quadric depend on U and V, right? Okay, this quadratic, yeah, P1, P2, P3, P4 is a characteristic covector. So this quadratic equation defines a 4 by 4 symmetric matrix, right? Coefficients of this quadratic form, right? We invert this matrix and we get a metric, symmetric matrix, but with low indices. This symmetric matrix defines you this metric or conformal structure, right? You can check that this metric is self-dual. Half of its Weil tensor is 0. And then we proved that all self-dual structures arise in this way, right? You can prove that all self-dual structures arise in this way. In fact, this, yeah, in fact, we proved this. It's in, this is contained in the same joint paper with Maciej Dunajski and Boris Kruplikov. There we described this kind of wrote this equation slightly differently, right? But it's an equivalent result. So all self-dual structures in 4 dimensions, they come from solutions of this equations, which we call conformal self-duality equations for this reason, because they define conformally self-dual metrics in 4 dimensions, right? And later I will consider the hierarchy of these equations. And this hierarchy will define as something else, scroll structures, right? Okay, now where the number 6 is coming from, right? So look, you have 3 second-order PDEs in 4 dimensions. Each second-order PDE depends it brings 3 arbitrary functions in the Cauchy data, right? 3 arbitrary functions. Sorry, what I'm saying. 2 arbitrary functions of 3 variables. Each second-order PDE gives 2 arbitrary functions of 3 variables, right? And there are 3 PDEs, so 6 arbitrary functions. This gives this number, this result of Grossman, 6 arbitrary functions, right? So it's very obvious in this explicit parameterization, this number 6, right? Okay, we also have this Lux pair for this system, right? Dispersionless Lux pair. It also contains d by d lambda, differentiation by spectral parameter, and otherwise it's linear in spectral parameter. Lambda appears here and here, right? So it turns out that if you require that these vector fields form an integrable distribution, namely their commutator belongs to the span of these 2 vectors. In this particular example, the commutator is not identically 0. It belongs to the span, right? Then if you require this, then you recover this system, right? So integrability of distribution spanned by these 2 vector fields is equivalent to this system, right? Okay, now we are in 5 dimensions. X1, X2, X3, X4, and lambda. We're in 5-dimensional correspondence space. We add lambda to this space, right? And we have an integrable 2-dimensional distribution in 5 dimensions. It has integral surfaces, 2-dimensional surfaces. How many of them? They depend on 3 parameters because we are in 5 dimensions, right? 2-dimensional surfaces. If you want to foliate 5-dimensional space by 2-dimensional surfaces, you need a 3-parametric family, right? So we have 3-parametric family of integral surfaces of this distribution. Okay, let's project them down. As before, let's ignore this lambda. We project them down. Then we get 3-parametric surfaces in the original space of coordinates x1, x2, in this space, x1, x2, x3, x4. We get a 3-parametric family of surfaces. And you can easily check that they are null with respect to the metric. So this metric restricted to these surfaces is identically 0. Equivalently, you can check that if you evaluate this metric on these vector fields, on xx or xy or yy, you get 0, right? So metric vanishes on these surfaces. These are Penrose's null surfaces. So in fact, Penrose's null surfaces are equivalent in this sense to the existence of a Lax pair, right? Okay, so in other words, conformal self-duality equations is a master system for self-dual geometry in 4 dimensions. Okay, and now I am moving to new results. What is involutive scroll geometry? Let me start with, first of all, what is scroll? First, I will define algebraic variety that is called a scroll. It's something very, very simple. So the easiest example is in P3. Let's take projective space P3. And let's take skew lines, two lines that are skew to each other, right? Maybe I can draw. Let me actually draw. I have in P3, yeah, I have two skew lines, two lines that are kind of skew. I parameterize them by one and the same parameter lambda, because what is a line? It's just P1, right? P1. I can parameterize it linearly by lambda. And I parameterize the second by the same parameter lambda, because these are just two different P1s embedded into P3. Right? So I parameterize these lines by one and the same parameter lambda. And then what I do, I just connect corresponding points. So to each point on this, they correspond some point on this. And I connect the corresponding points by lines. Right? In this way, I get a one parameter family of lines. And clearly, they define me a quadric surface, right? And these two lines, two initial skew lines, are just two particular rectilinear generators of the quadric from different families, right? So I get a quadric. So this is the simplest scroll, which is defined as 1, 1. S11, right? So 1 is, because this line is one-dimensional, so this line is kind of degree 1 submanifold, and this line is degree 1 submanifold. It's called S11. Now, what is S12? Now let me go to P. I'll define then everything in general, but let's go to P4, right? P4. And what I do in P4, I take a line and I take a skew two-dimensional plane. A two-dimensional plane that is skew to this line, right? So they do not intersect. This line doesn't intersect this plane. I can have this in P4. And in this plane, I take a conic. Okay, I take a conic, some conic, right? In this plane. So this has degree 1, and this has degree 2. Now we'll define what is called scroll S12. S12. So what I do, I parameterize this line by lambda. It's a P1, right? It's a P1 embedded in P4. What is a conic? It's also a P1 embedded in P4, right? This is parameterized by lambda linearly. This is parameterized by lambda quadratically. So coordinates will depend on lambda quadratic, right? And then I do the same as before. I take two corresponding points corresponding to the same parameter, and I join them by a line. And I take the union of all such lines. The union of all such lines give me a scroll surface, which I call S12. Right? It's a scroll. It has degree 3. This is a quadric. It has degree 2. Right? In general, what is a scroll? It's a ruled surface in projective space, two-dimensional surface, which consists of a one-parameter family of lines, which is smooth, no singular points, and which has degree 1 by 1 less than the dimension of projective space. So you see, degree 2 in P3 is a quadric. Degree 3 in P4 is this scroll, which is called S12. In general, a scroll is a smooth algebraic ruled surface in Pn of degree n minus 1. Now, how are they in general? How can they be described? There is a complete classification of these scrolls, of these surfaces. Now I come to a general picture. Okay, let me erase this first. Erase this. Okay, now I come to the general picture where we have projective space Pn, right? Pn, and we take two complementary subspaces, projective subspaces, Pk and Pl. Like you can think of the, oh, what's that? How do I get rid of this? Okay, we take Pk and Pl, right, of complementary dimensions, so they do not intersect. So you can think of just linear space, and you take two skew subspaces, linear subspaces, which span the space, right? So n equals k plus l plus 1. Remember, in P3, n is 3. I took P1 and P1. So 3 equals 1 plus 1 plus 1, right, and so on. Okay, you take Pk and Pl. In Pk, you take a rational normal curve of degree k. What does it mean? It's a curve with parametric, which is described by in coordinates as 1, as lambda, lambda squared, lambda cubed, so on, up to lambda k. Rational normal curve, right, of degree k. And in this PL, you take a rational normal curve of degree L. Okay, they are parameterized by lambda, by one and the same parameter lambda, right? This has degree k coordinates in lambda. This has degree L coordinates in lambda, right? And then you join points of these curves corresponding to the same value of the parameter. You get a one parameter family of planes. You can check that this is called rational normal scroll SKL. Before we described S11 and S12, right? So SKL is a smooth ruled surface of degree n minus 1, and there is what Del Pezzo's theorem says. It's an old stuff, very classical algebraic geometry. The Del Pezzo's theorem states that scrolls SKL constructed above are the only smooth, irreducible rolled surfaces of this degree k plus l in which is n minus 1, which span Pn. So the only such surfaces are these scrolls. Okay, this is just simple algebraic geometry, classical algebraic geometry picture, rational normal scrolls. Now, what is a scroll structure on a manifold? Imagine now we have n plus 1 dimensional manifold M. And then you take its cotangent bundle, Pt star M. And in each cotangent space, you define a rational normal scroll, right? Which varies from point to point, all right? So it's a family of ruled, irreducible, smooth ruled surfaces of degree n and of degree n minus 1 in cotangent space, Pt star M. So actually what I will need is not this general kind of abstract definition. We can think of it in a simple way. We can forget about what I said, right? Let's just introduce two differential forms in this manifold M. Omega of lambda, it's a differential form of degree k in lambda. Omega 0 plus lambda omega 1 plus 1 lambda k omega k, right? It's a form of degree k in the parameter lambda. And what is it? Omega 0, omega 1, omega k, just one forms on this manifold. Yeah. And we take another one form, phi 0 plus lambda phi 1 plus lambda to the L by L. Another one form, this time it depends on the parameter L up to degree, up to power L. Okay. And this phi 0, phi 1, phi L are also one forms, and they're all independent, linearly independent. So these omegas and phis all together, if you take them together, they form a coframe on them. So they form a basis of one forms on them. So, okay. And then involutive scroll structure, you can define like this. Alpha, some function, times omega of lambda, plus another function times beta of lambda. So a family of one forms of this type. So in other words, they depend on lambda and also two parameters, alpha and beta, right? This thing is kind of involutive, is a normal scroll, right? A normal scroll, right? A normal scroll structure, in other words, is just a pair of differential forms of this kind, right? You can forget about geometry. Just on a manifold, you have two differential forms of this kind, right? That's all. What does it mean that a scroll structure is involutive? It means the following. Now, let's fix a point on the manifold. Let's fix a point, and let's define two equations, omega of lambda equals 0 and phi of lambda equals 0. This equation, where lambda is fixed at this moment, let's fix lambda. Then these two equations define a codimension 2 subspace, right? Codimension 2 subspace in the tangent space of M. In the tangent space of M. Two differential forms vanishing. They define something of codimension 2, linear subspace in tangent space of M in Tm, right? And then when you vary lambda, you get a one parameter family of such subspaces. So when you write these equations, by these equations you define a one parameter family of alpha. I call these subspaces alpha subspaces, right? You get a one parameter family of alpha subspaces of codimension 2 in the tangent space of M, right? In other words, for every x in the tangent space of M at the point x, you have a one parameter family of codimension 2 subspaces. What does it mean then that this family is, it's like a generalization of a distribution. What is a distribution? At each point you have just one single subspace, right, of certain dimension, right? And here we have, at each point we have a one parameter family of distributions of certain dimension, right? Of codimension 2 in this case, right? So this is a scroll structure. That's all. The scroll structure is this. You have two forms of this kind, right? And you define this family of planes of codimension 2 at every point. This is a scroll structure. Okay, now what does it mean that the structure is involutive? It's a generalization of involutive distribution. What is involutive distribution? Suppose you have a distribution. You have a family of integral surfaces of the corresponding dimension, which are tangential to the planes of this distribution. And here it's something very similar. You should have a family of what we call alpha manifolds. So that alpha manifold is a manifold of codimension 2, right? Codimension 2, such that all its tangent subspaces are alpha subspaces, right? But not for one and the same value of lambda. Lambda is allowed to vary, right? So at every point, your submanifold should be tangential to one of these planes of codimension 2, right? At each point, we have one parameter family of planes of codimension 2, right? Parameterized by lambda. But now we forget about this lambda. We just have a one parameter family at each point, right? And so our submanifold must be tangential at each point to one of these planes, right? Not for the same lambda. maybe for different lambda, right? At different points for different lambda, right? These are called alpha manifolds. And we say that a scroll structure is involutive if every alpha subspace is tangential to some alpha manifold. Yeah. And the problem is how to classify all involutive scroll structures, right? And it turns out that there is a similar classification to what I showed before. There is a master system for them. And this is the hierarchy of conformal self-duality equations. So we don't have a full general proof in all dimensions, but we have a proof for S12 scroll structures and S22 scroll structures. S12 scroll structure is when you join points of a line and a conic. And S22 scroll structure is S22 scroll is when you join points of two conics, which are in projective correspondence, right? Okay, and then I think I have 5 minutes left, and I have 3 slides left, right? So I think I'll show these 3 slides.
Evgeny, you have you have at least half an hour if you need it.
Probably less, certainly less.
As you say.
Yeah. Okay. So involutive. Now I will show you. Actually, maybe this will be enough, just this, because the rest is okay. I'll show you a few more slides. So S12 involutive S12 scroll structures by heavenly hierarchy. So again, let me go back. We say that a scroll structure is involutive if it has this alpha manifolds, sufficiently many alpha manifolds, right? So we will see that these alpha manifolds come from Lax pair of a certain system, Lax equations of a certain system. Okay, what is the general structure of involutive S12 scroll structures? Okay, so okay, this is an example. Sorry, this is not a general form. It's just an example. Let's consider these 3 equations. This is the first heavenly equation. And these are 2 so-called modified heavenly equations. The first and the third are modified heavenly equations. Now we are in 5 dimensions. So x1, x2, x3, x4, x5 are independent variables, but u is one and the same. U is a function of 5 variables. It satisfies these 3 equations, right? These equations are involutive, right? They are compatible because this is one and the same hierarchy. They belong to the hierarchy of the first heavenly equation. They all commute, right, with each other, right? So what is the characteristic variety of this triple of equations for one and the same function? This is the intersection of 3 quadrics. Each equation brings this quadratic equation. This PD brings this quadric. This PD brings this quadric. So, and I need the intersection. I solve them simultaneously, right? You see the coefficients depend on this U, right? The coefficients of the quadrics, right? It turns out that I can parameterize this set, parameterize in this form. So PIs, I want to parameterize these PIs that solve these equations. I claim that PI dxi, this general characteristic covector, is alpha times omega of lambda plus beta times phi of lambda, where alpha, beta, and lambda are parameters, 3 parameters, and omega of lambda is this, and phi of lambda is this, right? You see, omega of lambda is linear in lambda, phi of lambda is quadratic in lambda. It has lambda and lambda squared. All right? So this is like a linear generator. This is quadratic generator, right? And I take the linear combination. I kind of. I connect. What this formula means? I connect points of this. I connect this and this corresponding to the same value of lambda, right? So geometrically, it means I connect a line it's parameterized linearly by lambda, and the conic, which is parameterized quadratically by lambda. This is what it means geometrically, but formally it's just a linear combination of these two differential forms, right? Okay, and the claim is that if U satisfies these equations, then this structure, so omega of lambda and phi of lambda, define me a scroll structure. This structure will be involutive. All right. So what are these equations? Omega of lambda equals phi of lambda equals 0. This is a three-dimensional distribution spanned by these vector fields, by these three vector fields. All right. Because it's three-dimensional, right? Codimension 2 in 5 dimensions means three-dimensional, right? And these three vector fields are nothing but Lax equations for these three, right? The Lax equations for these three are precisely these three vector fields, right? If you commute them, you get these three equations. So these three equations, this distribution, these three vector fields, they define a distribution in a three-dimensional distribution in 5 dimensions. So it has this distribution, it depends on lambda, for every lambda, right? It has three-dimensional integral manifolds. And you can show that these integral manifolds are alpha manifolds. On these manifolds, omega and phi vanish, right? So this, therefore, since there are alpha manifolds, this S12 scroll structure is involutive, right? According to the previously given definition. So, in other words, these equations give me involutive scroll structures of type S12, but not all of them. Now let me show you a construction that gives all of them. Right? It's a generalization. I'll have a generalization of these equations. Right? It will be a little more complicated. Now, how to obtain all of them? Now I take this, I start with these Lax equations. If you take the first two, forget about Z. If you take the first two, then it's exactly what I already showed for self-duality equations in 4 dimensions, right? Remember, we had three functions, u, v, and w. I'll show you the slide. Yeah, sorry. This. Yeah, these two vector fields. These two vector fields are precisely the same as it's the Lax pair for this conformal self-duality equations. So now I take these two vector fields and I construct the hierarchy of these equations. Okay, I go back to that slide. Okay, this x and y are the same, and I add another vector field. This hierarchy was constructed by Lenya Bogdanov, right? In particular, this vector field is taken from his paper. Right? So now I commute these vector fields. I take their commutators. I require that distribution spanned by them is involutive. This D, the span, is involutive. This gives me a system of differential equations for U, V, and W, right? And there are 9 second-order PDEs for U, V, and W. They're not terribly bad. Yes, sir, they're not really bad, but there are 9 of them, so I decided not to write them. All right? 9 quite simple-looking equations, I would say, right? For UV, for 3 functions. 9 equations for 3 functions. Here on the previous slide, look, I had 3 equations for 1 function. And here I have 9 equations for 3 functions, right? And they have a characteristic variety. And this characteristic variety, I can parameterize as follows. Alpha times omega of lambda plus beta times phi of lambda, where omega of lambda is linear in lambda, phi of lambda is quadratic in lambda, right? You have lambda squared, lambda, and here just linear in lambda, right? And here we have a theorem that all involutive S12 scroll structures arise in this way. So they arise from solutions of the conformal self-dual, of the hierarchy of conformal self-duality equations, right? And if you take higher floors, if you have higher floors of these conformal self-duality equations, you'll be getting higher involutive scroll structures. So you can view this as like geometric interpretation of self-dual hierarchy. So self-duality equations themselves, they generate self-dual metrics. So what the hierarchy generates? Okay, it generates involutive scroll structures, right? Okay, and if you look at this 9 PDs, right, for UV and W, you can calculate the freedom in the general solution. You'll get 9 arbitrary functions of 3 variables. So these structures depend on 9 arbitrary functions of 3 variables. Now, I'll show you 2 more slides quickly. Now, what about involutive S22 scroll structures? It's very similar. Now you take the previous 3 vector fields, the first 3, the same 3 as on the previous page, and you add a new one, W, right? And you ask that the corresponding distribution spanned by all 3 of them is involutive. Involutive four-dimensional distribution. I'm sorry, okay. So there are 18 of such PDs, right? 18 of such PDs. And the corresponding characteristic variety is a linear combination of these, where omega of lambda is this, phi of lambda is this. This time, omega and phi are both quadratic in lambda. So this is S22 scroll structure. And all S22 scroll structures locally can be obtained in this way, right? They come from solutions of this hierarchy. And you can count the freedom in these 18 PDs for UV and W, and you get 12 arbitrary functions of 3 variables. And the last slide, I'm really sorry, it's a bit dense maybe, but the last slide. Involutive scroll structures via the general Heavenly hierarchy. This is the general Heavenly hierarchy, which was introduced by Bogdanov. And this is a family of equations for one and the same. I'm really sorry, I will switch the phone off. Someone is very persistent. Okay, so I have one function u, this time of n variables, of n plus 1 variables, right? And for this function u, for every 4 out of this n plus 1 variables, I have this PD, right? A's are just constants, n plus 1 arbitrary constants. So I have a collection of 4-dimensional PDs for one and the same function. This time, how many of them? Many as there are C of n plus 1, choose n plus 1, 4, right? Choose n plus 1, 4. 4 out of n plus 1 indices, right? So for each of these, and you take all of them, right? This system is an involution. It forms the general Heavenly hierarchy, right? According to Lonya Bogdanov. Okay, each of these equations contributes its own equation to the characteristic variety. It contributes this. And you take a kind of a union of all these equations. Right? It turns out that the union of all these equations, for n equals 3, they define just a quadric. I'm sorry, my talk hasn't finished. I'll call you. So for n equals 3, we obtain this scroll. So for n equals 3, we have just one single equation, and this is a quadric, right? For n equals 4 and n equals 5, we have the scrolls S12 and S22. For n even and odd, we have scrolls this and this, respectively, right? But we don't have like a general statement that all scrolls of this type or this type come from the hierarchy of conformal self-duality equations. We believe this is true, but it's quite tricky to prove. There are difficulties in this proof, right? But what is a bit surprising, that all examples we know, they only give scrolls either of this type of this type. And we never get scrolls where the difference between this K and L, SKL, is more than 1, right? We never get scrolls, for example, of the type 1, 3, 2, 4, 2, 5, this kind of scrolls. For some reason, they never appear on solutions of S-characteristic varieties of solutions of multidimensional PDEs. This is kind of a mystery for me. I don't understand why. We try to classify involutive scrolls of type, say, 1, 3, and we get some kind of inconsistency. So it turns out that there aren't many of them. For some reason, there are quite a few scrolls of type S2, 3, or S12, but there aren't many of type S13. What's the reason for this? I don't know. Possibly we made a mistake, but at least there are no examples of scrolls SKL with the difference of these two bigger than 1, and I don't know the reason for this. Okay, I'll stop here. Thank you very much.
Thank you, Zhenya. It was interesting questions, remarks, comments. Okay, it was quite clear and very interesting. Thank you very much. So thank you for joining our seminar. Next Wednesday will be the last session in this year. So to those who will not be here, I wish a happy forthcoming New Year. And after the next Wednesday, we shall meet already in 2026. Goodbye, and have a nice holidays. Bye-bye.
Thank you, Yosif.